Alright, time for another draftphysics.com, debatephysics.com also, where there's a bunch of 5-minute videos kind of going over subjects like this, mgH versus mgT. So the simple argument I'm making is that physics is sort of just lying to itself. It's, kind of playing a silly game to think height is what causes the effect, that gravity is somehow a distance-dependent force, when it's obviously a time-dependent force, and just like other objects that do the same thing as gravity have the inverse square law as their function, like a light bulb. It's just pretty much, how long you're exposed to the light and how much light is hitting you. That'll decide how much you're going to move based on that pressure. So in the gravity case, it's an overt pressure, and you're going to be moved on based on how long you're in a field of gravity, a place where there's a gravitational differential. Those words really shouldn't confuse anybody. I mean, it really is a differential, okay, in some kind of mechanism. Whether you want to think of it as a bent geodesic or not, well, who cares? The point is that if you're in different places, you're in a difference. There's a difference between one side of you and the other side of you, and that's really what's causing the effect. There's more pressure, influence, whatever. Alright, so erase that. So one of the simple arguments, I think it's the simplest, and it also gets to a second subject, which is how we measure kinetic energy and all of that, is Galileo. So I should be able to figure out where to put this. Yeah, so there's an object, and we're going to drop it. And no matter where or how we drop it, that is, whether we drop it on a slope, that is, we have it roll down a slope, or we just drop it, it's always going to do this thing, okay, where it's going to drop a certain distance, and then it's going to drop another distance in a unit of time. And there's going to be this 1, 3, and you can keep going if you want, but you really just need the 1, 3 part. Will tell you all you need to know. It goes 5, 7. You're just accruing velocity. That is, your velocity is increasing as you go further because there's nothing inhibiting it. Now, in the case of a slope, there is an inhibiting factor, but the inhibiting factor is friction, and the friction is, in a sense, linear based on your exposure, again, to the gravity. So the gravity is causing the friction, and because gravity is causing the friction, it's going to also duplicate the 1, 3, 5 thing in terms of the less time you're in the gravity per foot, the less you're going to be pushed by the gravity. Okay, so this is the argument of sliding across thin ice. The faster you can go across the thin ice, the less chances you fall through the ice. The slower you go, the more chance there is you fall through it. And why is that? Well, because you functionally weigh less. You're reducing your weight. The pressure gravity is putting into you is less because you spent less time in it per foot. So it's always a time-dependent force. Now, this 1, 3 thing is basically telling you that you have acquired, half your velocity here. So if this whole thing took 2 seconds, you could understand that it's just 1 second worth of gravity here, and 1 second for this whole section here. And it kind of just proves the time-dependent element, that clearly the speed you're traveling is proportional. It's not linear. So the fact is that if you push something up against gravity, do the opposite, you give something a velocity up into gravity, you're going to go half your speed, 1/3, 2/3 of the way, no, 3/4, sorry, 3/4 of the way up is where you're going to go half your velocity. Now, that can't be explained as mgH. mgH fails here, okay, in the sense that obviously this distance is going to be very different than this distance, and yet the same effect on your velocity. In this whole thing here, you have exactly the same effect on your velocity as you have here. So whether you're accelerating or decelerating, the fact is it's always going to do this. Okay, and that means that how else could it be understood? The elemental function is time. It's about this 1 second and this 1 second. That's what's deciding. You're getting 9.8 per second. There's a second here, this little tiny amount of distance. Here's a second here, this big giant part of the distance. It's clearly saying the elemental function, the real function, is not height, it's time. Time is the real function. Well, mgT, instead of moving it. Yeah, that's the real function. And it's demonstrated right there in a simple example. And so we've been over this example again. So this one is, you know, on its face, it's very convincing of something, and then, you know, it doesn't take much analysis though to figure out what's happening. So I'm just going to roll something, okay, with a velocity. I'm going to give this one twice the velocity, and it's going to end up rolling 4 times as far, maybe even further. Well, you can't see the 4. I gotta figure out where the end of this thing is. Okay, that's where it is. So it's going to go 4 times the distance. But what's going to happen is it's going to be right here is going to be half the speed again, half the velocity here. Not here at half the distance. Here at 3/4 of the distance. I mean, clearly, again, time is in control. This will be 1 second of travel. This will be the 2nd second of travel. Okay, 4 times the distance, but only 2 seconds, 2 units of time. And you know I'm going to hit with 2 units of force. 2 units of time, 2 units of weight, in the sense that that's all it can weigh is twice as much. It's only going twice as fast. You know, this whole canard that somehow I should be concerned to think the elemental that each inch of distance is taking the same friction when it's not. I'm going very fast across this part of the ice, and I'm going very slow across this part. And the fact is that if it was a thin piece of ice, you could see the difference. I crash through over here, and I don't crash through over here because I'm going faster through it. I'm not collecting as much gravity per foot. I'm not applying as much weight to the surface. I'm not losing as much of the electricity because I'm not making very good contact. If I used an electrical example, I have a very poor contact with the surface here. I have a very strong contact with the surface over here. Therefore, I'm going to convey more watts of electricity through that contact. So again, kind of a decisive argument. If I think it's an absolute truth that half the velocity is here. If it's true, how can you argue that distance is what's controlling how much force? The amount of force is being controlled by the amount of time, not the amount of distance. Time is the elemental part. All right, now you can take this a more complicated step further, where, you know, when you're using a slope, the trick is, or let's say you're using a pulley, okay, and you're pulling something, okay, with a rope, and then dropping an object, you know. Those 2 examples, what time is going to tell you is that you're increasing by pulling something. You're creating all of this friction. You're not letting it free fall. So if it would have taken 1 second to fall, okay, if you let it free fall, it's not going to take 1 second when you're pulling something. You're dragging it. You're stopping it from falling in 1 second. So now it's going to be in the gravity much longer. It could be 4 seconds, could be 5, could be 10 seconds. The longer it's in the gravity, technically, the more force you're collecting from the gravity. You're holding the weight against falling. So then again, time is in control in the sense you can know the amount of time you can spend, this object can spend in the gravity will tell you how much force you're going to be putting on this cart, okay, to move it. And so the longer you can keep the stuff in the gravity, okay, the more force you can collect. But the downside is you're giving this thing velocity, so you're allowing it to free fall. So you can't have it both ways. Obviously, as this starts to move faster, this will free fall faster. So as you give it velocity, you're also taking away the time you can collect more force. So it's always limited, because your ability to put force on the object is limited by how much distance you're allowed to fall. And if you use up your distance, you can't apply any more time. Okay. Then with the rolling thing, the trick is you know, the amount of energy you get here at the bottom. First, you're converting energy down into energy sideways, and you're also storing the energy in the rotation of the object. So it's got a bunch of internal energy. So obviously you can't just use the height, or you can't just use the time, unless you're just doing it for relative comparisons. If you want to compare this height to this height, you can use the time, or you can use the height to get two answers. But you're not going to get an absolute answer by just saying how high is it, because you really do have to figure out that it's going to be more complicated than just how high is it, because it's going to matter how much mass it has and how much mass is caught up in the angular rotation. So you're going to get more energy out of the same thing based on, again, the mass, but half the mass, half of the energy is going to be stored in the spinning of the object, not just its actual velocity in a direction. So its linear velocity is only part of the energy it has. So that's obviously a more complicated experiment. Alright, so I don't think, I'll just reiterate for the sake of argument, it's just this simple. Okay, if it's true that this is half the velocity here of anything's travel, that it's going to travel with those proportions. So I can make that 10 miles, I can make that any distance, and it's going to reach half its velocity 3/4 or 1/4 of the voyage. So obviously these two distances are not doing the same thing. These two distances are doing something quite different, in the sense that per foot I'm gaining a lot less change than I gained here. I gained a lot of change in that short distance, and I gained very little change in this giant distance, clearly indicating that the thing that matters is that this is 1 second and this is 1 second. And as Newton stated, it's 9.8 meters. Well, 0.8 meters per 1 second. So it really is a time-dependent force. It's stated right here. It's a time-dependent force, not a distant-dependent force. Distance is only coincidentally associated with time, and especially when you just start with zero velocity. So as soon as I give objects velocity coming in, this mgH idea really falls apart, because now you're going to go through the gravity much faster, and so you're still going to acquire the gravity in the same way, but the amount of time you're going to be spending in the gravity is going to be greatly reduced. And so the contribution gravity will make to your final velocity and your final impact wattage is going to be minor. Alright, so I don't think I need to make any more arguments than that. I mean, I could do the ones I've already done, and then you could just turn off the video and say I've already heard those over and over again, so you don't have to bother. But just in case there's somebody who hasn't seen all of these arguments over and over again, you know, I'll just redo it again. Okay, so you have a gravitational body, and you're going to travel from point A to point B, or from point B to point A, either way. And the simple truth is that the faster you go will decide how much the gravity influences you. The distance won't make any difference, really. I mean, it makes a difference, it's a fact. But the distance isn't the elemental function. The distance doesn't say everything gets affected because this distance exists, and this distance is true, and this distance will tell you how much gravity there is. It won't. How much gravity So it's just like a light. You could just argue that it's just like this was photons. And all you're really saying is the faster I go through the photons, the less tanned I get. The slower I go, the more tanned I get. And if we just say how tanned you get, how many photons hit you, decides whether you crash into the earth or whether you go about your way getting to where you want to go. So the faster you go, the less gravity you get hit by. Clearly indicating it's a time-dependent force. Clearly indicating it's just like spray paint. The faster you go through the spray paint, the less paint gets on you. It's that simple. Gravity's doing exactly the same thing. I'm saying that's an absolute fact. It's been a fact forever. It'll be a fact forever. I'm just looking for somebody to explain how it's not a fact, how there's a single piece of evidence anywhere indicating that it's not a fact. Alright, so let's do this again. So just in case horizontal motion confuses you, you can do the same thing this way. Point A to point B, and you just have two things travel. One thing's going 50 miles an hour, one thing's going 500 miles an hour. Simple truth is, the thing going 500 miles an hour, I could say it would take 1 second to travel the distance. 1 second. And the thing going 50, let's just say it's 8 seconds. Okay, something like that. So it's going to be a big difference in how long they're going to be in the gravity. And when the one going 500 miles hits the earth, all it's going to go is 509.8. So it's only got 1 second worth of gravity. Same exact distance, it got plus 9.8. That's all it got. This one got 8 seconds worth, so let's just say 90 miles an hour added to its velocity, so it's going 140 when it hits. It gained, okay, the 90. So one gained 90, one gained only 10. Same distance. Obviously distance is going to give you the right answer. Time gives you the right answer, not distance. Alright. So we'll call that a video and such. Yeah. But we need a physicist to explain how there's something broken in here, because nobody else can do it. So we need somebody to just make the simple argument how I said something, how I drew something here that was incorrect, that wasn't representative of the truth. Till the next time, but can't find anybody. Nobody.